Okay guys, so we're going to be reviewing descriptive statistics and graphical statistics in this set of slides, and then really we'll be ending with, in this section, the inferential statistics that you'll see on the certification exam. So we'll start with just some basics here. When we have data collected, one of the first things you need to recognize is how we tend to organize data within statistics. Each column within this data matrix is a variable, so notice the student number, which is kind of an identification number, the gender, a variable recording whether they're an introvert or extrovert, and then also a dread variable, how much dread they have with regard to math class, perhaps, is another variable. But notice there are also rows within this data matrix, and each of these are observations, or in this case you can think of these as individual students. So student 1 is a male who's an extrovert and has a level of dread of 3, versus student 4 who's female extrovert, level of dread of 4. When we look at those different variables, we like to classify them, and this helps us understand better how to analyze the data in applied settings. So first of all, every single variable we see will either be numerical or categorical. Categorical are variables that fit into categories, simply enough. Numerical are things that are measurement variables or counting variables. Then further, to delineate, numerical variables are continuous, or what I often like to call actually measurement variables. And discrete, which can be thought of as counting variables. So you math majors out there, this would include also countably infinite sets. So let's do a little practice here. We have these variables here. Let's focus in on the first one here, gender. So gender is a category. You're either going to be categorized as being a male or a female. So we would call this categorical. We're not going to get more specific than that, but we could call this a nominal level variable as well, because of the fact that we're providing a name to classify people. Also sleep. It's the number of hours of sleep per night. So notice this could be numerical. I would call it continuous, although most people will report whole number hours because we don't tend to say, oh, I slept 7.48 hours last night. We tend to round it down or up to what we think we slept. Then also a bedtime. Notice that this is given within a time range. So for instance, on person number 1, observation 1, they're saying their bedtime is between midnight and 2 a.m. So this should be considered categorical, but it can be ordered, which is an ordinal level of variable. For example, the reason why I say it could be ordered is observation 1 has a later bedtime than observation 2, person number 2. Finally, let's go to the countries variable. This is going to be numerical, and it's counting how many countries they have visited, and so this would be discrete. It's a countable set. There's no, well, there would be an upper bound to this, but we wouldn't necessarily assume we knew what the upper bound was. Finally, dread would be categorical, and we would call that more specifically ordinal because the levels of dread ranges anywhere from 1 up to 5. Okay, so in the last video we went over variables and levels of measurement of variables, and let's do a practice here of that. So here I have a telephone area code, and I want to know what level of measurement is that, or what type of variable is that. I'll give you a moment to think, or pause the video. And that would be categorical. So an area code doesn't have any numerical ordering implicit in it, and it's really just common to a region. So we would call that a categorical, but not a categorical ordinal. Ordinal would imply that 915 is somehow greater than, say, 575, and that's not true. That's just different regions. When we take measures, we often want to assess, are there relationships between the variables? This is something that does come up on the exam. And in particular, I'd like you to take a look at this plot here and think about whether or not there's a relationship between the number of hours of studying per week and GPA. We would hope that there's something. The more you study, the higher your GPA presumably is. First of all, you might think about where you think a regression line might fit. You might think about, does it belong in the middle of the points? Does it belong in a place where it hits the most points? In general, since I don't have the ability to interact with you here, I'll say that we're going to assume that least squares regression line is going to be the one that fits in the middle of the point. So about as many points are above the line as are below the line. I'm going to actually kind of sketch that in. Now this isn't meant to be perfect here, but, oh, and look how imperfect that is. I was very wobbly with my line. But what we want to see is that roughly about the same number are above that are below that line. And what I'd like you to notice now is, do we see any unusual data points? For example, there is this value right here. At least at UTEP, you can't have above a 4.0. So we would assume that that's a mistake, an error in data entry. Also, we have a few unusual points that are probably not mistakes, but just unusual observations. Okay, so this is an error here, whereas these are kind of unusual in that the subjects here studied an unusually large number of hours per week. And when we look at some of a scatter plot like this, we want to first pay attention to those points. Another thing that I want you to pay attention to is the idea of the residual. Okay, so for a given observation, I just put a dot down there over one of the blue points. That vertical distance between the regression line and the actual observed point is what we call the residual. And it's just a measure of the error. And you may not have seen, particularly if you were in the track where you took the probability sequence of courses, you would not have come across this concept yet of a residual. And a residual in general is going to be the observation, which I'll denote yi, minus the predicted point. Now I gave you a little bit of formal regression notation here, but really this is the observation minus the predicted. And that's all we're doing here. So one thing I'd like you to note is that the residual of this first point, let's call this point A, would be much greater than the residual of, say, this point, point B. And so when we assess the fit of a least squares regression line, we want the fit that minimizes the sum of these squared residuals and makes that sum of these squared residuals as small as possible. That's the reason why it fits within the middle of a cloud of points. So let's practice this. Based upon this scatter plot, which is looking at head length and skull width, which statement do you think is correct? I'll give you a moment, or pause the video. And here you want to notice the fact that head length and skull width are going to be positively associated. I'll do my best again to draw a straight line, but if we were to draw that least squares line that is in the middle of the cloud of points, it might look something like that. There's some unusual points, but that doesn't invalidate the least squares line. It's just unusual points. All right, so in this next section of the descriptive and inferential statistics part of the notes, we're going to be talking about association between variables, whether or not we can call variables dependent or independent, and then we'll get at some design issues of when we can say certain effects cause other effects and when we cannot. So anytime we see any kind of dependency between variables, we say that they're associated. That's really the same term. Dependent is really describing association between variables. If they are not associated, there's no connection between the two, that we call them independent variables. So independent means whether or not one occurs, it doesn't affect whether another occurs. So let's use a context to understand this better. Early in the 1930s and 40s, people started to be suspicious of cigarette smoking and started noticing that people who smoked were getting sick more often, perhaps getting lung cancer more often. Yet there were often people who were naysayers about this. They relied upon anecdotal evidence, such as, well, my uncle smoked 3 packs a day and he's in perfect health. Well, over time, though, researchers and the research community at large was able to collect evidence that smoking has a very strong effect on your health and many negative health impacts, and that became clearer as time went on. So we saw this association, but sometimes, based upon that anecdotal evidence, it appeared to conflict that what we now know is a strong association between smoking and negative health effects. Okay, so part of how we approach understanding associations is first we have to explore data and take a look at data. We call this exploratory analysis. I like to think of this as a kind of a cooking demonstration, okay? Say you're cooking a pot of stew, okay? As you cook, any good cook is constantly tasting their food as they cook. And what you'll tend to do is you'll stir the pot and then take a small part of what you're cooking to get an idea about how the dish tastes as a whole. When you just taste a little spoonful and you decide whether or not it's, you know, flavorful enough or salty enough, we call this is akin to exploratory analysis. But if you generalize and infer that the entire pot of soup needs more flavor or more salt, then that's what we call an inference. So notice the difference. Exploratory is just assessing that small sample, that spoonful of soup. Whereas inference says, well, if this small sample is not salty enough, then perhaps that whole pot of soup is also not salty enough. And so we're inferring. But in order for that inference to be correct, we need to know that that small taste of the soup, that spoonful of the soup, is representative, meaning it really is a good snapshot of the population, your whole pot of soup. So suppose your soup has sat boiling for a while and you just, without stirring, skim off a part of the top. Perhaps that is extra watery or maybe has a coating of oil on the top, and it's probably not going to taste like the rest of the pot tastes. But if you first stir your soup and then take a taste, you'll get something that's more representative of the whole. And this gets us to this idea of bias. So if we only skimmed off the surface, we'd be getting a bias sample. It wouldn't look like or taste like the rest of the soup. Versus if we stir and get a good representation of the soup, we are not going to have any sampling bias. Now, when you actually do data collection, there are 3 types of sampling bias you're going to need to know about on this certification exam. There's the non-response bias, when only a tiny fraction of people choose to respond, and that tiny fraction tends to not be representative of the population. A tiny fraction of people, by the way, can respond, and if they're representative, that's often okay. A voluntary response, though, occurs when people respond to, say, a poll or something, and do so on a voluntary basis. This will tend to not be representative of the population. You'll tend to get people who feel strongly about the issue, one way or the other. And finally, the convenience sample, those just easy to access. All right, so last time I got cut short on that last screencast video, and so let's review really really briefly here. The non-response bias, the voluntary response bias, and the convenient sample bias are ways we get samples that are not going to be a good representation. So this is, again, similar to not stirring your pot of soup before you take a sample, okay? What we ideally want is a sample that really looks like our population, and each of these three kinds of sampling will not give us something most of the time that looks like our population. I'd like to illustrate this really briefly just to also bring up another point, a common misconception I see with students, okay? So in 1936, Landon sought the Republican presidential nomination. He was running in opposition to FDR. During the election, a magazine that was very popular at the time called the Literary Digest did a poll. They got 2.4 million Americans to respond, which at that time was a good, a large proportion of the American population. Their poll suggested that Landon would be the overwhelming winner over FDR. However, when the election was actually held, FDR won with a landslide. Okay, so what was wrong here? They had a huge sample size, but they were completely wrong. And by the way, because of this poll, the magazine was really discredited and was soon discontinued. Well, how did they survey? That's the first thing you need to suggest or investigate to see why this went so poorly. They surveyed their own readers, registered automobile owners, as well as telephone users. At that time, remember, this is during the Great Depression. So there was a large proportion of people who did not have the ability to subscribe to something like Literary Digest, did not own an automobile or a telephone. And those tended to be the people who were more affected by the Great Depression, who were more likely to vote, say, for FDR. Those who did have access to cars and telephones and subscribed to a magazine like Literary Digest tended to be wealthier and tended to vote more Republican. And so they actually got something that was unrepresentative of the U.S. population at that time, and that's why their polling, even though they had a very large sample size, was just wrong. And so I point this example out because large samples are good, but if they're biased, it's still useless data. And on the same token, a small sample you may think of as bad, but if it's a good snapshot or representation of the population, it can still be very useful, even if it's a small sample. So what matters more is not the sample size when you collect data, but whether or not your data collection is introducing a bias. So let's think about here how which of these is true, and think about issues of bias when you read this scenario. Go ahead and pause the video and read over it. So I hope that you paused the video and read and thought about this a while, but which of the following statements are likely to be true? Well, it would have to be 1 and 3. 1 being that some of the mailings may have never reached the parents, which is certainly always true. And then also that many parents of the high school students could still be disagreeing because maybe the ones who did not respond or did not get the mailings are the ones who disagree with this policy change. And so you need to be able to recognize in applied situations when sampling bias may be introduced in a data collection process. This is the kind of problem that, or application I should say, that you might see on those certification exams. So before we talk about measuring variability for samples, I want us to do this more conceptual activity on variation. And this is very much aligned with some of what they ask you in the certification exams. I happen to believe strongly in recognizing variation visually, which is really the intent of this application. So here I have 5 sections of a class, and each of those classes took a quiz, and the quiz could be scored anywhere from a 0 up to 10. There were 10 questions, and you got credit for each question you got right. So 0 to 10 for the range of scores. And what I want to ask you here is, which class do you see the largest variation or variability in quiz scores? Now, I could ask you here which class has the largest standard deviation. That's the same question here. We'll talk about why in the next set of slides. So for just a moment, think about that. Which section do you think is the most variable, and why do you think? Now what we may want to emphasize though is actually the graphical representations of these classes. So for example here we have the same data, but now we have them plotted in bar charts. So we can visually see what those scores look like. So for example, Class A is unimodal with a very prominent peak right at 5. Class B is bimodal with 2 peaks at 1 and 10. Class C is definitely uniform. Class D is, well, there's a lot of choppiness to the bars. I'd say it's fairly unimodal, and Class E is very unimodal, but not as prominent at the modal region of 5. So which one would have the largest standard deviation or variance? Well, some of you may be looking at criterion, for instance, how far they span. And Class C, definitely, we see every score from 0 up to 10. So there's the widest range of scores. But that's not actually how we measure variation. What we tend to do is measure distance from the central measure. In this case, that's the mean. So we might draw in, what does that mean look like? Or where would it be for each of these distributions? So for Class A, it's about at 5. It's at 5.9 or so for Class B. And then 5 for everything else. And what you want to really pay attention to is which of these has the most observations that deviate significantly from that mean measure. Okay? And what you'll see is we really may want to just contrast. Let me get back up there. Classes A and B just for a moment. A has a mean right at 5, a very prominent modal region. So very few of the observations deviate significantly from the mean, which is 5. In contrast, Class B has really basically no observations that are right at the mean, which is 5.9, and many of the observations with the peaks at 1 and 10 deviate significantly. So we'd say Class B has the largest variation or standard deviation. Okay? In contrast, Class A has the smallest. So smallest there and largest here. Those are the main things that you're going to need to understand for the certification exam, is how that variation is related to deviations from the mean, and be able to pick out the largest and say smallest standard deviation or variance for a set of plotted data like this. So now we're going to talk more formally about the variance. So what we hopefully got from that variation activity was that deviation from the mean is what matters most with regard to measurement of variation, or the variance. So you can see here that the variance formula is the sum of the squared deviations about the mean. I don't perceive that using this formula is all that important on the exam, but you can see how it plays out here for this particular set of data. So we see some observations that deviate significantly and some observations that deviate only a little bit, and they contribute different amounts of variation depending on how far they deviate from that mean, that sample mean. So we often square use the square or we do use the square deviations to calculate the variance, and this has a very practical purpose. It gets rid of the negatives so that the observations that are equidistant from the mean are equally weighted, and it also weighs those larger deviations more heavily. So this also points out one reason why the variance is not the preferred measure of variation when you have heavily skewed data, because it will be inflated. Now, the standard deviation is just the square root of that variance. So for that same data set from before, the variation was 4.11, and we simply square root that number to get 2.03. That's why on the variation activity, I said I could ask you which has the largest variance or which has the largest standard deviation. I'm really asking the same question there. No difference. Another measure of central tendency that we haven't talked about yet is the median, and the median basically splits the data in half so that 50% is above it and 50% is below. When we have an even number of observations, it's very easy to find the median. We simply order the observations from least to greatest and find that central value. In this case, with this simple set, it's 2. But when we have an even number of observations, it's a little bit more difficult. You simply order the observations, but then you need to take the 2 central values, and convention is to take the mean of those central values. It doesn't actually need to be the mean. It could be any point between 2 and 3. And that's because any point between 2 and 3 gives you 50% above and 50% below. So there's also these quartiles that we need to understand in order to fully understand box plots, which is the last plot we'll be looking at. The first quartile is what we call the 25th percentile. That means 25% of observations are below it and 75% are above. The median or second quartile, Q2, is the point at which 50% are above and 50% are below. You will see that called Q2 sometimes. And then the third quartile, Q3, is the point where 75% are below and 25% of the points are above. And then when we talk about an interquartile range, which is another measure of variation, it's simply the difference between the third and first quartiles. This is particularly useful when we have highly skewed data. So a box plot makes use of all of these measures that we've been talking about previously, and it gives us a sense of the 50% middle of the data. Also, it gives us a sense of where the median is as well as where outliers are. The components of the box plot are the following. Okay, we have that box which begins and ends at the first and third quartile. The median's in the center. The lower whisker and upper whisker tell you where we expect to see observations. So any points beyond the lower and upper whiskers are suspected outliers. And this is one way of determining when a point is likely a statistical outlier or not. I don't perceive that they're going to want you to actually compute this, so I'll go over this pretty quickly. What they really want you to understand on the exam is the interpretation, pinpointing outliers, pinpointing where the middle 50% of the data is, and where the median is. So one application of all of these measures of variation and measures of center that you'll need to know for the certification exam is understanding how sample statistics such as the mean, median, standard deviation or variance, and IQR would be affected if there are particular values of outliers. So for example, if the largest value of household income, there we go, was replaced with 10 million, then how would these various measures be affected? Okay, so think about that for a moment, because the mean would be pulled upward because every single point matters and gets weighted equally. Whereas the median is simply the center of the data. So whether or not the highest observation is 10 million or 100 million or 100,000 doesn't really actually matter. The median is robust to outlying points. In the similar way, the variance would be inflated with an extreme outlier, whereas the IQR would not, because those first and third quartiles are not affected by outlying values. So we can see that laid out here for some specific distributions. When we have something that's symmetric, as in this first diagram, the mean and median are roughly about the same. Okay, and that's because the mean and median, the mean's not going to be pulled to the left or to the right by outlying observations, because we have about an equally number of low observations as we do high observations. But if we see right skewness in data, we will see that the mean gets pulled towards those larger observations, so the mean will be greater than the median. Here you can see the mean in the blue dotted line, dashed line, and the mean in the green solid line. In contrast to the left skewed distribution, the mean will be smaller than the median because it gets pulled downward towards these lower observations, since each observation is equally weighted. Okay, so let's apply this here. Let me move this also. I have a spacing issue. There we go. Which is most likely true for the distribution of the percentage of time actually spent taking notes in class versus being on Facebook, Twitter, or other social media outlets? So take a moment. Think about which of these are going to be true, most likely. Well, I would make the claim that the mean is going to be smaller than the median here. The mean's going to be pulled down by these low observations where certain people had very low percentages of time. A majority of people had high percentages of time. So the median was 76%, while the median was 80%. So we see the effect of those outlined to the left observations on these measures of central tendency. When we have extremely skewed distribution, it becomes such a problem sometimes that we make transformations to the data. The most simple and effective one is the log transformation, and there are various reasons that I'm not going to get into why a log transformation is so useful in so many different settings. But just take a look at this example. We have the number of basketball games attended. So, you know, within a particular season, maybe you go to 1 or 2 and that's it, and you'd be in the majority if that was the case. If we make a log transform of that data, we can observe the data in a way where we can make more distinctions about the variation between, say, people that attend 1 to 2 games versus, say, 6 to 7 games or so on. Now, there's always a pro and con of making a transformation. We tend to only do it in the case of extreme skewness, and that's mostly because it's a little difficult to then interpret the model once you get done when you make a transformation. But in cases where data is extremely skewed, it's a very useful tool. By the way, this comes up, the idea of the log transform, I saw on just one question on the certification exam, and I wanted you to be aware of the role of transformations of variables. So when we have 2 or more categorical variables, we'll often organize them in a contingency table, and a contingency table is just a way of visualizing the data or the distribution of the data for 2 or more of these variables. So here we have 2 categorical variables, the gender of a person and whether or not they're looking for a spouse. And we can see, for example, that there are 86 females that are not looking for a spouse and 51 females that are looking for a spouse out of the total of 137 females. Another way to look at this is maybe there are 51 females that are looking for a spouse and 18 males that are looking for a spouse out of the total number of students, 69 that are looking for a spouse. Now, contingency tables, like I said, are useful when we have categorical data, but so are bar plots. We've already seen one bar plot on that on a previous example, but here's a couple of different views of bar plots. They look like a histogram, but they're different because notice we don't have ranges of continuous measurement data on the x-axis. Instead, on the x-axis, we have categories. So the categories may be male or female. They might be ordinal, so counts, 1, 2, 3, and 4. But they are always going to be categories. Now, when we have data that's categorical, we often summarize the data using proportions. For example, we might want to look at the percent of females looking for a spouse. Well, that's 51 out of 137. Now, many students will make the mistake of making this 51 out of 207, but that would be the proportion of students who are female and looking for a spouse rather than the percentage of females who are looking for a spouse. So it's important to identify the part and the whole. So here the part is spouse and the whole is females. And so you put your part in the numerator and your whole in the denominator. Similarly, the percentage of males looking for a spouse would be 18 over 70. So your part is whether or not they're looking for a spouse. Your whole is the male population. Another way to display data that's a little bit more complex than when we have relationships between these categorical variables is using these segmented bar or mosaic plots. So notice here we have, again, the same data, but we have a little bit more detail here with these plots because we can see the proportion of females to males, but also the proportion of females in the light blue that are looking for a spouse versus not in the dark blue, and same thing for males. This is a mosaic plot where we can really compare, and we can see, yeah, a little bit more females are looking for a spouse than males perhaps. Pie charts are another way to graphically display categorical data. This one I'm assuming you're familiar with. Also, when we have categorical data that's a grouping variable, such as your classification in school, we might do so-called side-by-side box plots. So we have maybe displays in the number of clubs the student is associated with, and then their classification. Okay, so now we're going to be looking at confidence intervals, and the first thing I really like to talk about with students when I start talking about confidence intervals is the so-called margin of error, and that's because most of you have seen this before. So I'm going to present here a common way margin of error gets talked about in the media. Here we have a general public survey where they did some telephone interviews of some people, and highlighted in blue towards the bottom it says margin of sampling error is plus or minus 2.9 percentage points for results based upon the total sample and 4.4 percentage points for adults aged 18 to 34 at the 95% confidence level. So this is often how things get reported in the media, but I want to give you how statisticians read and understand these results, okay? So this is saying that that proportion who agree that young people in the United States are having a tough time in today's economy is 41% plus or minus that margin of error of 2.9%. So if I were going to write this out, I'd say something like we are 95% confident that the interval 3.8.1%, which is 41 minus 2.9, up to 43.9, which is 41 plus 2.9, of the public believe young adults are having the toughest time in today's economy. The other one is 49% plus or minus 4.4. That interpretation would be we are 95% confidence that between 44.6 and 53.4% of 8 to 14-year-olds have taken a job they didn't want to pay. They didn't want to just to pay the bills. Okay, so I'm being very loose with my interpretations here, really, I'd say I'd be 95% confident that these intervals capture the true value of the proportion of young adults who are having a tough time or have taken a job just to pay bills. But I'm not going to emphasize those technical things here and just give you that general interpretation of the margin of error instead. Okay, and this all fits within the context of parameter estimation. So we often want to know, for example, what is the true proportion of young adults who have, say, taken a job that they really don't want just because they need to pay the bills? And we need to estimate it some way. Okay? We can do that in a lot of different ways, but first we need a good sample. And that representative sample that we can use simple random sampling or cluster sampling or stratified sample will give us sample statistics, which are these point estimators for the thing we want to know about. But we need to recognize that every time we take a sample, that there's variation introduced by the sampling itself. So if you go out and survey some people on a topic and your best friend goes out and surveys some people on a different topic, you'll end up with different results. Not because the truth is different for you versus your friend, but just due to sampling variability. And that's why we characterize this variation using a quantity called the margin of error. And what that margin of error shows us is it quantifies how large that sampling variability is for that particular collection of data. Okay, so let's think about a question here. Suppose we randomly sample 1,000 adults from each state in the United States. What would you expect the sample means of their heights to be? The same, somewhat different, or very different? So let's say you take a sample of 1,000 adults, your best friend also takes that sample. Would you expect your sample means to be the same, somewhat different, or very different? And we should say that they're not going to be the same, but only very slightly, because if you're both getting good representations of the population, the only thing that will affect them being different is sampling variation. You will get a different sampled set of individuals than your friend will, which will lead to different sample measures. Okay, so I want to do an application here that's going to mimic an activity that in my classes when I teach this, I usually take one class period at least to really drive this point home for students, because this is really important. So make sure you understand this. Here we have a histogram that is the distribution of the number of drinks it takes some group of college students to get drunk, get intoxicated. So we see everything from, well, a little bit above 0, you have to drink something. Some people, I wonder about those people choosing 10. But we might have some questions such as which values are most likely to be selected and which are least likely, and what affects that. Okay, so in order to understand this more thoroughly, I've laid out kind of a table here. Okay, let's say we don't have access to the population, so we can't survey every single college student of our population and ask them how many drinks does it take you to get drunk. So we only have sample data, which is almost all the time. That's the case almost all the time. Rarely do we have access to a population. So in order to really get a sense of the average number of drinks it takes college students to get drunk, we might sample from the population and use our sample mean as a best guess for that population mean that we want to know something about but is inherently unknowable. Okay, so we might sample with replacement 10 students from the population and record the number of drinks it takes them to get drunk. Then we find that sample mean and plot the distribution of the sample averages. Now, I do a similar activity with students when I teach, except I actually have groups of students, and each of them gets their own random sample. We plot it together, and then we can even use simulation to see if we continued this process over and over and over, what would it look like? And I'll show you that in the next video set. Okay, but here I'm just going to show you perhaps the results of one group. So let's say one group got a set of random numbers listed there, and so those are their observations. So they get those observations and find the sample mean. And the sample mean number of drinks it takes a college student to get drunk according to their collected data is 5.9. Now, it just so happens, since this is a somewhat manufactured example, that the true population mean of the data is 5.39. So notice 5.9 is somewhat close to 5.39. It's not on the dot, it's not exact, but that is the true mean. mu. Their data resulted in x bar of 5.9, and it's pretty close. And usually when I have multiple groups get this, we can see, wow, okay, most of our sample means are fairly close to that population mean. And then we start forming them all together, so we get this thing called a sampling distribution, where we plot those sample means up on a board or on a display all together, so we get this thing called a sampling distribution. Now, in the next video, I'm going to show you a simulation that will mimic what I do with students in class to construct this idea of a sampling distribution. Okay, so this is an online applet. You can get to this if you go to onlinestatbook.com, and they have a collection of applets there. But what I really want to illustrate is this idea of constructing a sampling distribution here. So here I'm starting with a unimodal normal distribution. This is a so-called bell curve distribution. We haven't really gotten to this yet, but notice it's symmetric and unimodal, and we give that a special name, the normal distribution. And what I want to show you again is, just like with our example that we just looked at in the previous video, we can take data. So let's say I have each of you collect a sample of size 5 from the parent population, and this parent population is this gray distribution up here. So I could have one person do that, and that would be their 5 points, which leads to that sample mean plotted here in blue. Okay, so those 5 observations have a sample mean of that. I could have another student do it. They would get a different sample, random sample of the data, which then results in a different sample mean. We could do that many, many times, and here that process becomes clear, that every time a new sample of data is obtained, we get a distinct sample mean. And we could do this many times, or I could do it 5 times in a row, or I could even do it 10,000 times in a row. And notice how I'm getting a distribution of those sample means that we can really characterize as having certain characteristics, such as it's symmetric and unimodal and looks much like that parent population, except it has less variation, because notice there are less observations that vary from that modal region or the mean region. Okay, so we could do this for a normal distribution, or let's pick a skewed distribution. And we might think, how does this differ for a skewed distribution? I'm going to jump right to 10,000. And we see that that distribution, when we take samples of size 5 and plot those means there in blue, we also get something that looks much like the parent population, except it has less variation each time. Notice that just like the parent population was skewed to the right, this one's slightly skewed to the right. So something's going to change though if I change the sample size. So if I change this from n equal 5 to n equal 25 here, so that every time you collect a sample of the data and then compute that sample mean, it's not based upon 5 observations, but upon 25 instead, as animated here, then we're going to get a set of means that come from these samples of size 25, and notice the effect it has on that sampling distribution. There's even less variation than we saw before, so a further reduction in the variability. Notice there's more observations grouped about that modal region or the mean for the distribution, and we really don't see signs of skewness anymore in that distribution here in blue. Okay, now in the next slide, this is what we call the sampling distribution, this thing in blue. And it's the sampling distribution specifically for the mean. And we have interest in the mean because that's going to help us make inferences about the population mean. Because we know that for large sets of observations, that sample mean is going to have something that's near normal, like we have here. Symmetric and bell-shaped, and can be characterized by something we call the normal distribution. And that gets me to this slide here. And I'm gonna end with this slide because it really characterizes what we saw in that simulation. Each time, I didn't emphasize this, but each time the mean remained the same, the mean of that distribution. But this variation, or what we call the standard error, which is the standard deviation for the sampling distribution, was reduced each time, and reduced as a factor of the square root of n. So we'll start here on the next slide. So using that applet, we saw that the sample mean is going to be well approximated by something that looks like a normal distribution, something that's unimodal and symmetric. And in fact, the mean and the variation or standard deviation of that sampling distribution for the sample mean is characterized by the mean of the original population and the standard deviation of the original population divided by the square root of n. And we can see this given by this formula here. Now, SE stands for standard error, which is simply the standard deviation of the sampling distribution. When sigma is unknown, we simply put in the sample standard deviation, S. Now, when we see a sampling distribution and it's symmetric and centered about the population mean, that's not an accident. That happens anytime n is large enough. And how large is large, you may ask? Well, usually a good cutoff rule of thumb is n bigger than 30. And this will ensure that we have something near normal that is characterized by this mean and this standard deviation. As the sample size increases, though, we expect more consistent sample means, and hence that standard error here is going to get smaller and smaller and smaller as that n increases. Notice it has an inverse relationship. So in order to apply the central limit theorem, which was characterized on that previous slide, we have a few conditions. First of all, independence. The sampled observations need to be independent. If random sampling and assignments used, that's generally going to be true. If sampling's done without replacement, well, as long as your sample size is less than 10% of the population, you're probably fine. But what we tend to pay a lot of attention to also is the sample size and skewness. If the population you're sampling from is very, very skewed, we need a really large sample size in order to believe that the central limit theorem applies. Usually 30 will do for slightly skewed distributions. For highly skewed, we may need 50 or so observations. For moderately skewed, we say 30 works. So finally, we get to confidence intervals, and I like to talk about confidence intervals after describing sampling distributions because there's a really nice tie-in there. So I like to first describe confidence interval as being a plausible range of values for a certain population parameter. The main reason we use confidence interval is it's, quote, casting a wider net. So imagine trying to fish. Okay, you could go out and spearfish, but there's a reason why most people are not spear fishermen. You have a high probability of missing. If you are even slightly off from your target, the fish, you're going to miss. Okay, so it's a very difficult objective to be on the spot. Versus if you use a net for fishing, you have a wide area and you have a really good chance of catching fish. And I like that analogy because it really gets at why we don't just always use point estimates. When you have a point estimate, like in our previous example, our point estimate was 5.9. We didn't hit the mark on the head. Our population mean was 5.39 rather than 5.9, so we were wrong. But if we computed a confidence interval, we are very likely to capture that true value of 5.39. So this is a nice analogy for why we like to use a confidence interval for reporting a plausible range of values for capturing a particular value. And we're going to emphasize the mean because that is what's emphasized on the exam. So first we're going to use an application of a confidence interval. Here we have a setting. A random sample of 50 college students were asked how many exclusive relationships they've been in so far. We got a sample mean of 3.2, so on average 3.2 relationships, and a standard deviation of 1.7. Let me point out here, obviously, none of the students had 3.2 relationships. That's impossible. But 3.2 should be interpreted as a long-run average of the number of exclusive relationships. So we'd expect a lot of the students to be reporting that they had 3 exclusive relationships, or maybe 4, and maybe there are a good number that said 2, but maybe perhaps not so many that said 0, and not so many that said, I don't know, 15. And the standard deviation, again, is going to be a measure of how far those observations vary from that numerical mean. Okay? And we want to know, what is the true number of exclusive relationships? And we're going to use a confidence interval to answer that question here. So a confidence interval can be approximated using this formula. And this is really what you're going to need to know on the exam. This is the general form that applies almost, well, for anything on the exam, it will be using this formulation. So you use a point estimate. A point estimate for the mean is x bar, the sample mean, and then plus or minus that margin of error. So this 2 times the standard error is the margin of error, okay? And we get that by computing first the standard error and then using a 2, which is actually an approximation of the true critical value, which is based upon a standard normal distribution. But I'm skipping those details because you really don't need that for the certification exam. So plugging in our values here, our sample mean was 3.2. So then we have 3.2 plus or minus 2 times the standard error, which is 0.25, because we took 1.74 over the square root of 50. That gives us a plausible range of values of 2.7 to 3.7, and our margin of error was 0.5. So let's apply this. Which of the following is a correct interpretation of the confidence interval? I want you to pay attention to which interpretation is reflecting the fact that this confidence interval gives a plausible range of values for the true mean number of relationships, and which ones are saying something really different than that. So pause this, take a look. And the answer would be B. College students on average have been in between 2.7 and 3.7 exclusive relationships. So this is saying on average, meaning the mean. That's important there. Let's point out what's wrong with the others. Okay. Well, the first one, A, it says the average number of exclusive relationships college students in this sample have been in is between 2.7 and 3.7. Well, everything's good until you get to this phrase, in this sample. We already know all about this sample. It has a mean of 3.2 and a standard deviation of 1.74. Enough said. We know about the sample. What we want to be able to do is infer to the population. So that's wrong because the focus is not on the population. C says a randomly chosen college student has been in between 2.7 and 3.7 exclusive relationships. So notice it's not making reference to the mean number in any way, and it's making a prediction about if you randomly selected a college student, what would be true. So C is wrong for that reason. And then D, 95% of college students have been in 2.7 to 3.7 exclusive relationships. That is making a claim about the sampling distribution rather than the mean. So that first illustration of the confidence interval, I told you it was an approximation. We can be a little bit more accurate, be a little more exact by using, in place of 2, a z quantile. And I'm not going to go a lot into this because I am not reviewing a lot of detail about the standard normal distribution, but I am going to say that 2 is pretty close to this standard normal quantile that gives us 95% of the observations between those values. That value is actually 1.96. When we use an interval like this, again, this is reviewing some of the assumptions for applying the central limit theorem. We need our observations to be independent. We need a large enough sample size to deal with the skewness in the parent population. And And that makes, you need to be thinking about these issues anytime you construct a confidence interval. I'd like to get into a little bit more about what does confidence, that claim of confidence really mean. So when we say we are 95% confidence, what does that really mean? So again, going back to that more general formulation, where the margin of error is 2 times the standard error, we would be able to make the claim that in about 95% of the time that we make intervals using this method, that we would capture the true population mean. So here, the mean, or the true value for the population mean, is denoted by this line right there. Okay? And you can see most of the time that value of the mean is included as part of the range of the values reported for a confidence interval estimator. But we have one miss. Here's a miss. Okay? And when we have a 95% confidence interval, we're saying approximately 5% of the time we're going to miss that parameter. We'd have a case where the interval does not cover it. Unfortunately, we never know if we're missing or hitting the right value when we compute an interval. All we know is that 95% of the time it will be accurately covering the true population parameter. So the width of the interval is really important to think about. I like this Garfield cartoon because it really illustrates why we want to think about interval width in practical applied settings. So taking a look at tomorrow's weather, there will be a high temperature that's between 40 below and 200 above. And Garfield says, this guy's never wrong. Well, of course he's never wrong because he gave an interval so wide that it really didn't tell us anything and covered all possibilities that we would pretty much ever see. So when we want to report an interval, we want it to be wide enough to have a large degree of confidence and to have a high probability of capturing that population parameter, but we don't want it to be so wide that a person goes, well, yeah, but you've told me nothing about what I need to know. So we need it to be informative. Okay? And so that's really affected. The width of the interval is directly related to that margin of error. And so recall, that quantity right here is the margin of error, okay, that we add and subtract to our point estimator. In order to change the confidence interval, we'd have to adjust that critical point, Z star. I'm not going to talk in detail about it, but just tell you that the most common value is 1.96. Lower values of Z give you lower degrees of confidence. Higher values of Z give you higher degrees of confidence. One more slide. Okay, so I got cut off on that last video, but one more thing I would like to say is sample size also affects that margin of error and hence the width of a confidence interval. So we recall that standard error here is the standard deviation divided by the square root of n. So if we're using the sample data to estimate this standard error, we'd use S over square root of n. So what happens if n gets bigger? Okay, you'd see a decrease in your standard error when n gets larger, which would mean a decrease in your interval width. So the higher your sample size, the smaller or the narrower the width of your interval. Okay, so as n increases, then the width decreases. But as the sample size decreases, the width would increase. So we can see that those relationships between the critical point and the sample size really come into play with that margin of error. That's where you need to, what you need to think about when you think about how, say, increasing the sample size would affect the width of an interval, or increasing the level of confidence would increase the width of an interval, and so on. Okay, so that really finishes up the confidence interval stuff, and now we'll get to an application. Okay, so this is an example I like to use when I teach. Really, the intent of this example is to focus in on whether or not gender here affects promotion rates. So we see here with this data that 21 out of 24 males, or 88% of males, were promoted, whereas 14 out of 24 females, or 58% of females, were promoted. So I give this activity to my students and ask them, do you believe that promotion and gender are independent or dependent? Here, independent would mean there's no discrimination based upon gender, and so the observed difference of 88% and 58%, that 30-point difference, is really just due to chance alone. It just so happened that less females were promoted than males, but it really had nothing to do with discrimination. Versus, if you believe they are dependent, then you'd be making the claim that there is gender discrimination and that the difference in the proportion is not due to chance. And this gets to something that we need to think about as we start drawing about hypotheses for hypothesis testing. So the null assumption here is that we have independence. The alternative assumption is that we have dependence. Notice here, one or the other of these is true. Either there is gender discrimination or there is not. And also note that we're going to assume there is no gender discrimination until the data suggests otherwise. Okay? So this gets us at this idea of formulating hypotheses for testing. So we could construct a sampling distribution for that proportion or the difference of the proportions. Okay, so remember our difference of the proportion was 0.3. So I think actually I subtracted female minus male, so it would be a negative 0.3. So there would be our observed difference in the proportions. And here's the sampling distribution. So what we really need to figure out is that value in the sampling distribution unusual or not? Is it typical of what we'd see if there's no gender discrimination, or is it atypical of what we'd see? So when we start drawing our hypotheses, we need to recognize that the null hypothesis will give us the status quo, while the alternative hypothesis gives us what we're trying to figure out, what we're testing for, in other words. We always conduct our hypothesis test under the assumption of the null hypothesis. So we believe it is true until we have evidence against it. So if we simulate data or derive a test statistic, it is under that assumption of the null hypothesis. Then, if the data provides evidence against the null for the alternative, that's when we reject the null in favor of the alternative. So in the next set, we'll complete this material. So we're still focusing on hypothesis testing, but I'm going to give you two ways of reporting the results of a hypothesis test. I'm going to start with what we're more familiar with here, which is using a confidence interval. And a confidence interval can actually be used in a hypothesis testing framework. And I actually like it. When you test hypotheses using a confidence interval, you're really making the claim that a 95% or any other level of confidence interval is giving that plausible range of values for the true mean. So going back to that number of exclusive relationships that college students have been in, our plausible range of values was 2.7 to 3.7. So we're making the claim that 95% of the time an interval constructed in this manner will capture the true value of the true number of exclusive relationships. So what if we wanted to test the null assumption that college students have been in 3 exclusive relationships, given here in the null hypothesis, versus that they've been in more? So which do you think that this would support? Would this support the null hypothesis, that interval of 2.7 to 3.7, or do you think it gives evidence for the alternative? So there's some ambiguity here because you may be thinking, well, 3 is contained in that interval, but so are values greater than 3. So what do we do with that? Okay. Well, since the null value is included in the interval, we would fail to reject or not reject the null hypothesis. This is a really easy way to go about thinking about hypothesis testing. I'm presenting it to you first because you already know this idea of the confidence interval at this point. But what I'll get to next is the approach most commonly used in research settings, which is reporting the p-value. So here are a little bit different context. Here we have a survey asking college students how many colleges they applied to. Based upon a sample of 206 students, we got an average of 9.7 college applications with a standard deviation of 7. That seems large to me. The College Board website states that counselors recommend students apply to roughly 8 colleges. Does this provide convincing evidence that Duke students, which is the population from which our data was collected, is higher, apply to more than is recommended? So that's our research question. Let me go back actually to the previous slide. Let's formulate our hypotheses. So the research question is, do Duke students apply to more than 8? So that would go in as the alternative hypothesis because it's what we want to know, our research question. But we're going to believe what the College Board says, that they should apply to 8, and that mean is 8, unless we get evidence otherwise. So there's our null and alternative hypothesis based upon the research question. And we're going to report this using a p-value. So I'm going to really emphasize conceptual understanding of the p-value here. We calculate a test statistic, and then based upon the results of that test statistic, we get the so-called p-value. And it is the probability of observing data at least as favorable to the alternative hypothesis if the null assumption is true. Another way to say that is the p-value is the probability of obtaining data this or even more extreme if the null hypothesis is true. So when it's low, let's say less than 5%, we say it's very unlikely, and we would reject the null hypothesis saying it's unlikely to get data like this if the null hypothesis is true. But if the p-value is high, we say it's likely, and we would fail to reject the null hypothesis. So we're going to apply this in the next set of the video, or next part of the video, and see how a large versus small p-value affects our decision in a hypothesis testing framework. Okay, so I'm really going to show you what you're going to need to know on the exam, and skipping a lot of detail here. So if you took my course during a semester, you get so much more detail about where this all comes from. But I'm going to focus in on just the need to know stuff here. So the p-value, again, is that probability of observing data this or even more extreme under the assumption of the null hypothesis. So notice here, this is a probability calculation. This is saying, what's the probability of getting a sample mean greater than 9.7, which is what we observed as the sample mean number of college applications Duke students put in, if the null hypothesis really is 8. So notice we have here a conditional probability statement that we're using, the probability of this condition holding true if the null hypothesis is true, because that's reflecting the assumption of the null hypothesis. This gets translated into a z-score calculation. For those of you who know z-scores, I'll show you a little bit about where this comes from. If this doesn't mean anything to you, then don't worry about it. I don't remember my standard deviation. Let me flip back up here real quick. 7. Okay, so our standard deviation was 7, and there were 206 students surveyed. So notice this here is the standard error. So we take the deviation between what's observed and the null statement of 8 divided by the standard error, and that gives us that 3.4. Okay, and then we can find the probability of observing a 3.4 for a standard normal distribution, and this is the part I'm glossing over because I don't spend a ton of time talking about the standard normal distribution for this exam review because it doesn't come up directly. But there's a very low probability of getting something as extreme as 3.4 from a standard distribution. And in fact, it has a probability of 0.0003. So notice that this is smaller than 5%. There's only a 0.03% chance of observing a random sample of 206 students who apply to 9.7 or more schools if the null value really is 8 for the population we're sampling from. So this is pretty low. So we'd reject the null hypothesis and say probably Duke students do apply to more schools than just 8. The difference between the null value of 8 and the observed sample mean is not due to chance or sampling variability, but is due to real distinct differences, decisive differences between Duke students and other college student populations. So let's apply this to another problem. So take a look, pause your video, read through this, decide which one you think is correct. Okay, so here we would say reject H0. The data provides convincing evidence that college students sleep less than 7 hours on average. So why did we do that? Well, our p-value is 0.0485. So technically, because that is less than 5% or 0.05, we're rejecting the null hypothesis because that's a relatively small probability. So we'd be saying we only have a 4.85% chance of seeing data this or more extreme if they sleep really 7 hours a night. So we're going to reject that they do and say that they sleep less than 7 hours a night. Now, note that 4.85 is barely smaller than 5%, so I would call this a marginal result. And perhaps if we collected more data, we'd fail to reject the null hypothesis. So this happens at times, and which is why a p-value is important to report, because you can look at that as the person reading the results and go, well, that's a marginal result because it's barely below 5%. When we have a two-sided hypothesis test, meaning the alternative is two-sided, mu not equal, we just multiply our probability by 2. And that gives us both tail regions as the p-value, because any deviation, in this case away from 7, is deemed a departure from the null hypothesis. So if we're far away on the right or far away on the left, it's still a departure from the null hypothesis. All right, so that completes the hypothesis testing.